Hello.
Hello.
Hi. So previously we did about the Fourier transform, and in last class someone asked me about the frames and basis to elaborate some more detail. So I prepared for that. So in today's lecture we will see what is the frames and basis, difference between basis and frames also. So it is common that we have redundancy in common to in our daily life also, like we double check about or triple check that we turned off the gas or light, something like that. So if the same thing happens when we deal with some signal, so like the if any signal represented in another system, then we typically basis where it is character characteristics are more readily apparent in the transform coefficients. Okay, so however these representations are typically non-redundant, and thus corruption of, or loss of the transform coefficient can be serious. Okay, so in comes redundancy, we build a safety net into an representation so that we will avoid those uh, disasters. So the redundant counterparts of the basis is called the frames. Okay, so uh, the reason we try to represent our signal in a different domain is typically because the certain signal characteristics becomes obvious in that other domains, so facilitating various signal processing takes. For example, if we perform Fourier analysis to uncover the harmonic composition of a signal, if our signal happens to be a sum of finite number of tones, the Fourier domain representation will be non-zero at exactly those tones and will be zero at all other frequencies. Right? So however, if our signal is a sum of, say, a pure frequency and a pulse of very short duration, the Fourier transform will be an inefficient representation. So, before going to the frames, so first we need uh, what is the basis. So, basis is something you need to, like, we have some space, vector space, say V is some. We have vector space. Vector space, you know.
Yes.
Yes. So in every vector space, for to represent every vector in that vector space, there are some basis set from which we can represent the all vectors of the vector space. Then what is the property of this basis? This basis should be linearly independent, right? So the linearly independent vectors, like we have three-dimensional vector. uh, let's say one vector, uh, a vector is somewhat a x cap plus v y cap plus c z cap. Okay, so this vector we can represent like a comma v comma c. So this is the vector space. So the basis will be 0, 0, 1, 0, 1, 0, and 1, 0, 0. These three will be the basis of this vector space, all the vector space which in this xyz plane, all the vector will be represented with the help of these three, and these three are also linearly independent. So these are the basis set of this vector space. Okay, so but uh, this set will be more like 1, 1, 0, 0, 1, 1, or we can say 1, 0, 1. This can be also be the set of basis set of this vector space, but this will not be the linearly independent. Then it will call the frame for this one. This is the main. difference between the basis and the frames. Because this orthonormal basis, these are the linearly independent also. But if the linearly independency is basis, then it uh, known as the frame, not the basis set. Okay, so like uh, like a we have one subset like phi, which is psi I, where I belongs to some capital I. This is we consider some finite dimensional vector space. Okay, that is B. Then where I will be something like 1 comma 2 comma 3 dot 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 n. Okay, so if I have from 1 to n, then it is called n dimensional vector space. So a vector space V will be infinite dimensional if it contain an infinite linearly independent set of vectors. Okay, so it is also depends on the dimension of the vector. So if we equipped with a norm, then a subset this subset phi, which is psi I, where I belongs to I, so of B is called the basis. If for this called the basis of this vector space B, if for every x belongs to B, there exists unique scalar which is x. This is a scalar. I represent xi. So with such that x is equal to summation I belongs to I to xi and psi I. Then it is called the basis of this vector. So mm, and also one inner product, you know, the inner product of in of two vector in this vector space, which can be also defined x comma y, let's say these two vectors, then the inner product defined as summation uh, I belongs to I and xi y I star, where star is for the complex conjugate of this by I. So and the norm, like if we say the norm of some vector, then norm of this vector can be defined as xi multiplied by xi equal to summation I belongs to I xi mod square. Okay, so this is the norm one, and this orthonormal basis is defined as orthonormal basis we will define like this. If any phi which is equal to psi, where I belongs to I the same, then if two vectors from this one, this set, uh, let's say psi I and psi j, if this the inner product of this one equal to delta ij, where delta is canonical delta, which is 0 if I is not equal to j, then this set is called the orthonormal set. Okay, so this definition I think you know already. Just to remind, so if we take one example here, like suppose we have the orthonormal basis phi such that phi equal to 1 comma minus 1, t is denoted for the transpose upon root 2 and 1 comma 1 t upon root 2, then given that this basis and arbitrary vector x, like we have any arbitrary vector x in the plane, then what is the point in this new basis? So we have to find, like, we have, suppose that we have orthonormal basis like phi, then we change the coordinate, like we have any arbitrary vector x, then what will be the basis set for this set of vector like x? Okay, so how will you find? You have any idea? Like we have here x and arbitrary vector in some plane. We have one orthonormal set. Okay, here. So we have to find the new uh, this basis set for this new coordinate system. So for that, what we will do the projection x onto the new basis. Like suppose this x be consider 1 comma 0 transpose, then if we consider x phi 1, where phi 1 is this one and this is phi 2, so if we project this x on phi 1, then what get we will get x comma phi 1. We compute that projection like that. So what we will get, so we consider 1 comma 0 transpose comma phi 1. Phi 1 is 1 comma minus 1 by root 2. Okay, so how we will multiply? We multiply this one and this one, because this is like uh, what it is called dot product, like. Okay, so this will go 1 by root 2. Okay, so this will be our x phi 1. Similarly, if we find x phi 2, then we will also get this 1 by root 2, because now we take this phi 2 on the places of this phi 1 and then multiply again. Sorry, not here, here. Okay, not here. Then we will again get 1 by root 2. Okay, so thus in this new coordinate system, our point will be 1 0 transpose, and this becomes x phi is equal to x phi 1 and x phi 2. Okay, so and the transpose, so our x phi 1 is 1 comma 1 upon root 2. So uh, it is still the same point in the plane. We only read its coordinate depending on which basis we are considering. Okay, so we can express the above process of figuring out the coordinates in the new coordinate system, like capital X is equal to x phi. So this will be, we can consider x phi 1 and x phi 2. Okay, so x phi 1, how we will calculate? X into psi 1, right? And this we will be calculated x into psi 2. So if we open this these two. So how we will get this phi 11 x1 plus phi 12 x2 and phi 12 x1 plus phi 22 x2. Okay, so now if we split this matrix, so we will get psi 11 psi 12 psi 21 psi 22 and x1 x2. Okay, so this is we have 1 by root 2 1 minus 1 and 1 1, or this is x1 and x2. So we have here this phi star into x. Okay, so this this can be observed that this matrix phi describes an orthonormal basis in the real plane. The column of the matrix are basis. The column of this matrix are the basis vector, and the row is also we can consider the basis vector. So that is the process of finding coordinate of a vector in a different coordinate system can be conveniently represented using a matrix phi, which is here this one, whose columns are the new basis vector, that is x phi is equal to phi star into x. Okay, so example 2 we will take, we will show here DFT, that is called discrete Fourier transform. So this discrete Fourier transform is also an orthonormal basis expansion. Can you prove that? So like we consider this xk is equal to 1 upon n summation I is equal to 0 to n minus 1 xi, and this is wn ik, where k is equal to 0 to n minus 1. Like we know that that DFT, that is discrete Fourier transform, is uv ubiquitous. However, it is not traditionally looked upon as a signal expansion or written in the matrix form. The easiest way to show this DFT on an orthogonal basis to do that is to look at how the reconstruction is obtained. Okay, so this xk uh, is equal to 1 upon n, where this wn ik we consider e to the power j 2 pi by n. So this is the, we know, nth root of 1 or unity. In matrix notation, this we can write as x is equal to 1 upon n 1 1 2 1 and 1 wn dot 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 wn n minus 1, similarly till 1 wn n minus 1 till wn. Okay, so and next vector we can write x0 x1 dot 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 x n minus 1. So this is our x and this is our phi.
How we written matrix?
Hmm?
How the matrix form is written?
So here, like if you expand this one, So how we will get this x0 w0, okay, plus x1, this will be w1, okay. Similarly x2, and sorry, this I will go to I2 n minus 1, okay. I will expand here. So if you write this in the if you express this one, then xk you can write 1 by n summation we will open. So it will be x0, okay, from 0 if we take, and here will be w and I will be 0 k, okay. And similarly plus x1 w and 1k plus x2 w and this will be 2k, so on, okay. So this is something like dot product, okay. Now if you uh, multiply this one, so this will be x0 x0 x1 plus x, like that one. So this w and 0 k, it will be 1. Similarly if you open this one, so you will get this one 1 upon n. So like that you can say, like we have here xi, okay. So xi you can write in n dimension, x0 wn xn minus 1, right. And this wn ik you can write some matrix form in phi is equal to this one. Then you can multiply these two and you will get the same result. Have you understand?
Can you understand how you written that?
Which one? This one or this?
The matrix form, how the matrix
Matrix form. So like
how it expansion.
this is in the summation form, okay. So if you expand this I equal to 0 to n minus 1, so which term you will get 1 x 0, sorry x0 and x0 to x n minus 1,
Yeah,
okay.
yeah,
And in multiplication you will get w n 0, like you will get w n 0 k. So this w and I k is equal to the e to the power j 2 pi I n, okay. So this is the nth root. So you can write here e to the power j 2 pi y n. So this will um,
okay, we first also n is varying from what? N is also varying.
yeah, n is also varying from 0 to n minus 1.
N is no, n is how vary n minus one.
Hmm?
How n is varying n minus one. And if n is varying from one to like
Like this w I k is equal to uh, sorry, this is w n only, and this.
Sir, first we fix k equal to 0, then we expand I equal to 0 to n minus 1. The next 0 can be written in first column.
Yes. Actually, here this K will also vary, I think. This K will also
Again we
vary.
fix k equal to 1, then we expand in second column and so on in a column.
Yes, yes.
Same similar. Okay, okay.
But in this case, this DFT matrix, which is this one, is not normalized. Okay. So we have to normalize this. So for the in the normalization process, we will do n, and this dftn, which is the dimension of n, and we multiply again dftn, and it will come to this I. Then we can say this is normalized. Okay. So if we normalize it by 1 by root n, the DFT would exactly implement on the orthonormal basis. So the decomposition formula is usually keeps this decomposition formula is xi is equal to, this is k equal to 0 to n minus 1 xk wn minus ik, where I is equal to 0 to n minus 1. This actually, I think this formula is used to decompose this one into this. So this is the decomposition formula for mm this one. So and in this matrix notation, this X is something, this DFTN matrix, and this X here, this is X. We can again in this one. So in the in our basis, this would be phi is equal to something. This is psi, which we are considering again and again. I belongs to I. So what we take in the basis set. So this psi we will take somewhat 1 by root n, and w and 0 comma w and 1 dot 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 w and I n minus 1 transpose. So this will be our basis set. Then this expansion formula of this one, uh, this one can be seen like xi is equal to x comma phi I, like that. Okay. So the reconstruction formula like the x will be somewhat summation, and tends I tends to 0 to n minus 1 to xi and phi I, and this will become I tends to 0 to n minus 1 x comma phi I and phi I. So this will be our 1 by root n dftn star, and 1 by n root n dft into x. Now we saw that the notation of this basis in finite dimensional spaces implies that the number of representative vectors is the same as the dimension of the space. But when this number is larger, like we saw that the dimension of space if n, then number of vectors will also be n. Uh, okay, in the previous vector space and all these things. So when this number is larger, we can still have a representative set of vectors, except that the vectors are no longer in linear independent. Like if the dimension of vector space n and the number of dimension vector are will be same, then we can construct one space such that these vectors are linearly independent. All the vectors will be linearly independent. But in case when this number of vectors will increase from the dimension of this vector space, then we cannot choose all the vectors such that they are linearly independent. So if all the vectors are not the linearly independent in any vector space, then it is called frame. Then we called it as a frame, not the. Okay, so frames are signal representation tool which are redundant, and since they are less constrained than basis, they are used when more flexibility in choosing in a representation is needed. Got it?
Can you repeat it to me?
Okay. Like from there, the from frame to see the vector space dimension is n. Okay. Okay. I will write. So mm, when this number of sorry, when this number is larger, we can still have a representative set. Okay, but except that the vector will not remains the linearly independent. Okay, so this the resulting set is then called the frame. Okay, so the frames which representing this signal tool which are redundant, and since they are less constant, because uh, in that vector space they are all should be linearly independent. Okay, so this will be constant for us, but if we need more flexibility and less constraint, then we use this frame instead of this vector set. Okay, like for example, uh, we take one simple example. Consider this Hilbert space H, which is r to the power n or c to the power n, which is n dimensional. Okay, so we then define frame more formally that n. Uh, okay, take this example. Orthonormal basis. Let take one orthonormal basis. Add a vector to it and see what happens. Like suppose our system is given like that. This is, and this is another axis. Okay, you can say this is real and this is imaginary axis. So let's say this is 1, this is 1, and this is minus 1. Okay, so this one is phi 1, this is phi 2, and this is some phi 3. Okay, so this phi is something phi 1, phi 2, and phi 3. Okay, so this will be given something 1 comma 0 t, 0 comma 1 t, and 1 minus 1 t. Okay, so the first two vectors phi 1 and phi 2 are linearly independent, and these are orthonormal basis. Okay, and the third one, this is phi 3. uh, this is added to this orthonormal basis. Okay, in this case, So what can we say about such system? So okay, so the answer is like first it is clear that we have three vectors. Okay, three vectors in, and what is the dimension of this one? This is R2 space, right? You know this R2, R3, Rn means, because this is two dimensional only, 1 0 0 1 1 minus 1, then it is written as R2. If it is three dimensional, then it will be R3. Then there will be three component in this bracket. Okay, and similarly for Rn, this is n dimension. Okay, so uh, now because this is two dimensional, but the number of vectors is three. Okay, so this will be no more linearly all, because these two are linearly independent to each other, but now this one is added in this one. Now this phi 3 can be written in the form of some 1 comma 0 and 0 comma 1. Okay, so the linearly independent C is vanishes in this set of vector. Then we take this 3 1 2 3 1. Okay, so the you can write this, you can find this B, right? A and B, and get the coefficient. How can we write this phi 1 minus phi 2? Like if you get, then it will be phi 1 minus phi 3, because you will get A is equal to 1 and B equal to minus 1. Okay, so it is also clear that these three vector must be able to represent every vector in R2. These three one will also represent all vectors which is in R2. Okay, since their subset is able to do so, because these two, if we take only these two will also be able to represent produce all the vectors in this R2. But if we take these three one, then it will also be able to reproduce all the vectors in R2. Okay, so so if like some vector x, in other words, we know that this will be also following true, because x we can write some projection x on phi 1 first, and then phi 1 plus x projected on psi 2, and then psi 2. Okay, now we can add a 0 to this expression, something like this one. This one plus we can add this x comma phi 1 minus x, this will be this one, and minus phi 1 and phi 1 minus phi 2, which is equal to phi 3. So this can be also added. Okay, so if we arrange it slightly, then we will get x is equal to x comma 2 phi 1 into phi 1 plus x comma minus phi 1 plus phi 2 and phi 2, and third term we will get x comma minus phi 2. Then this will be the inner product, and it will be phi 1 minus phi 2, which is equal to phi 3. Okay, so in this above we can recognize that minus phi 1 plus phi 2 x minus phi 3. Okay, so and the vector inside the inner products we will call phi 1 bar is equal to 2 phi 1, and phi 2 is equal to minus phi 1 plus phi 2, and phi 3 is equal to minus phi 1. So these three phi uh, uh, can reproduce all the vectors in this space. So this will be the frame. Okay, and this frame also can be written in the form of matrix, like uh, we can rewrite this expression such that x to phi 1 we will take phi 1 bar, and this will be phi 1 plus x phi 2 bar, and this will be phi 2 plus x phi 3 bar, and this will be phi 3. Okay, so in summation form you can write I is equal to 1 to 3, and this will be x comma phi I and phi I. Okay, so now you can write the matrix form such that all these three vectors now, uh, these three will be in the form of row and column. Okay, so we can write 1 comma 0, 0 comma 1, and 1 and minus 1. Okay, so and phi var will be, if we write from here this two, this one and this one, then you will get 2 comma 0 minus 1 comma 1 and minus 1 comma 0. Okay, the only difference between these two expression and one for the general basis, the general basis is that matrix phi and phi bar. This matrix phi and this phi bar are now rectangular. Okay, so these are the frames, curl frames, not the vector set, orthonormal basis set. Okay, so now we can see that we started with the orthonormal basis, and adding a vector, we obtained another expansion with three vectors. Okay, so this expansion is reminiscent of the one for the general y orthonormal basis we have seen. So the vectors involved in the expansion are now linearly dependent. Okay, so this redundant set of vectors, which is phi, is called the frame, while this phi bar is called the dual frame. Okay, so this phi is the frame, then it will be the dual frame and dual frame. So how can we uh, picturize this like that? So it can be like phi 1, this will be another axis, this will be 1, this will be 2, this will be 1, and this will be minus 1. Okay, so if we denote phi 1, this is 2 comma 0. Okay, so this will go from here to here, this will be our phi 1 now. Okay, and this will be minus 1 to 1. Okay, so this can be this one phi 2, sorry, minus 1 comma 1, it will go somewhere here. Okay, so this will go to like that, and this minus 1 comma 0 will go to this one. So this will be phi 2 and this will be phi 3. So this will be the dual frame. Okay, one note is that in many text on the frame theory, if you see, the frame change is usually denoted by this phi and phi star, not phi star. Okay, this will not be. uh, so given that this phi and phi bar are interchangeable, we can use one or the other without risk of confusion. Okay, you can either choose this one or choose this one. Okay, so one more thing, like while this adding a vector work we did, we ended up with an expansion that does not look elegant because as it involves both the frames and it's dual as well. Okay, so is it possible to have frames which would somehow mimic orthonormal basis? To do that, let us think for a moment. What characterizes orthonormal basis? How about this? Like first thing is orthonormal basis are self-dual. Second thing is orthonormal basis preserve the norm. What do you think about these two questions? So these two questions can be given on the basis of first we consider simplest frame named Mercedes Benz frame. Okay, so what is this Benz frame? This is arguably that the most famous frame. This is the most famous frame you will see. It is a collection phi of three vectors in R2. This is the collection of three vectors in R2 and is an excellent representative for many class of frames. For example, is the simplest harmonic tight frame. Uh, like we consider one phi PTF is equal to some three vectors phi 1, phi 2 and phi 3. Okay, where the frame has been scaled so that this phi PTF and phi PTF star will be I square. Okay, because that means we considering this what it's called normalized one. Okay, so this phi PTF star we will have 0 root 2 by 3 minus 1 by root 2 and minus 1 by root 6, 1 by root 2 and minus 1 by root 6. We take this expression. So the expansion of this expression will be like we have some vector x which can be written as I equal to 1 to 3 uh, x comma phi I and phi n. Okay, so this should be equal to this phi PTF and phi PTF star into x. Okay, so if we find the norm, because we have to give this answer the norm one question answer, like so this norm x square, how we will get this I is equal to 1 to 3 and norm of x comma phi I inner product mod square. Okay, so this will be norm of small x also. So as we know that this PTF and star PDF is equal to I, then this phi PTF can represent any x from R square. Okay, because this is 1. So x from r square, which is the real frame, since this equation x, this equation x, the same set of vectors is used both for expansion and reconstruction. Okay, so phi PTF is the self dual. From here we can say like these two are same. So this phi PTF is also the self dual. Uh, so we can think of the expansion in this X3 not linearly independent anymore. Okay, as a generalized of the orthonormal basis, this one, except that the vector are not linearly independent anymore. So the frame of this type is called a tight frame, that is preservable tight. So we can normalize the length of all the frames vector to 1, that lead to the unit norm version. Okay, so if we do this phi unit norm vector, so we write un tf type function. This tf is the for the type frame. So this will be phi 1, phi 2 and phi 3. So as uh, now if you plot this one, this norm, this one, so this is 1, so this will be 0 comma 1 t, and other one is root 3 by 2 comma minus 1 by root 2, and other one was 1 by root 3 by 2 comma minus 1 by root 2, this one. So we have these three vectors to construct all the vectors in this frame. So this can be written phi u and tf is equal to root 3 by 2 phi ptf star. So it will come 0 minus root 3 by 2 root 3 by 2 and 1 minus 1 by 2 and minus 1 by 2. So this will go to some phi 1 star, phi 2 star and phi 3 star. Okay, so with the corresponding expression of this x will be x equal to 2 by 3 summation I is equal to 1 to 3 x comma phi 1, sorry phi I is equal to 2 by 3 phi u and tf and phi u and tf star into x. So similarly the norm you can write 2 by 3 norm of small x square. Okay, so now we can compare the expression into the orthonormal basis with the expansion onto the unit norm version, which is this one, has the extra scaling this thing. Okay, so in orthonormal you will get this is equal to this one, but here this factor is coming. So when this frame is tight and all the vectors have unit norm, as in this case, the inverse of this scaling factor denotes the redundancy. So the redundancy will be 3 by 2, or you can say 50% redundancy is there in this frame. Okay, so the more vector then needed to represent any vector in R square. So here you can note that in general relating the frame bounds to the redundancy factor does not seems to be possible for frames that are not tight. Okay, so the general frame, this is the last section. In the general frame, like if we see one figure, like this is all frames. Then we can divide it into one. So into one it will be ENF. So ENF is equal to something equal norm frames, and this will be TF, that is called tight frames. So this is some overview of the all types of frame, tight frames, and the cross section of these two will be E and TF, which is called equal non tight frames. Okay, equal non tight frames, and this another type of frames like it will comes inside this one. Mm, you can plot like that. So the frames in this section it is called UNF, which is denoted a unit norm frame, and this is PTF, which we write somewhere above. So this PTF is denoted for preservable tight frames. Okay, so this is PTF, this is UNF, and in between this one, if you say, so this is called UNTF. So it is UN for unit norm and TF for tight frame. So unit norm tight frames. Similarly, the ENPTF, this region, this is ENPTF. So it is called uh, equal non-preservable tight frames. Okay, and similarly, this region comes for ONV. This is called orthonormal basis. Okay, so maybe this picture will clear you what is the difference between orthonorm basis and all other type of frames, right? So some frame operators, some operators which represents this frame and all these things. Maybe we will cover in the next session.
आप
Okay.
जो ये पढ़ा रहे हैं मैम ने तो कुछ इसके बारे में पढ़ाया नहीं ये सारी चीजें
क्या
मैम ने लेक्चर्स में तो कुछ और ही पढ़ाया है
क्या पढ़ाया?
मतलब ये इससे जो आप मतलब एक्स्ट्रा करके बता रहे हैं मैम ने तो बहुत सारी चीजें अलग से बताई
लाइक मैंने एक्चुअली ये पूरा फ्रेम्स के ऊपर बनाया था, क्योंकि लास्ट टाइम वो एक लड़की ने पूछा था कि मेरे को थोड़ा फ्रेम के बारे में इवेलुएट कर देना कि क्या है।
वो तो अच्छा है मैम ने
हम्म,
मतलब बहुत सारा चीजें बता दिया था
इसीलिए मैंने एक्चुअली ये मतलब कि थोड़ा सा
बुक
बनाया था।
बुक रिकमेंड करें कौन सी बुक को
ये
स्टार्ट करते
ये वाला जो मैंने किया है मैं एक्चुअली ये भेज दूंगा आपको, जो
हैं
मैंने
ठीक है
पढ़ा है।
पीडीएफ
ये एक्चुअली मैंने एक पेपर से पढ़ा है।
अच्छा अच्छा ठीक है
हम्म,
ठीक है चलिए थैंक
आप मेरे को अपना जीमेल वगैरह कुछ दे सकते हैं ताकि मैं आपको सेंड कर
हाँ मैं
सकूँ।
जीमेल दे देता हूँ मैं जीमेल टाइप कर दे रहा हूँ
ओके ओके। हाँ
न्यू टॉपिक तो समझ नहीं आ रहा है
सॉरी।
न्यू टॉपिक तो समझ नहीं आ रहा है ये
हाँ,
अभी अच्छे से
थोड़ा सा एक्चुअली फ्रेम वगैरह में क्या है, वेक्टर स्पेस, और ये एक्चुअली मैम ने बहुत शॉर्ट में केवल वेक्टर स्पेस का थोड़ा इंट्रोडक्शन दिया है। उसके बाद सीधे फ्रेम का वर्डिंग वगैरह यूज किया है। उसके बाद अभी मैं नेक्स्ट वाला देखूंगा क्या है। तो अभी फ्रेम समझ में आया कि
मैंने मेल
फ्रेम्स।
भेज दिया है
ओके। ये जो मैं जहाँ पे सारी चीज़ शेयर करता हूँ, मे बी मैं यूट्यूब वाले में लिंक में डाल दूंगा ये वाला पेपर जो भी है।
ठीक है मैंने मेल भेज दिया वैसे आप भेजना चाहे तो इस पर
ओके
भेज
ओके ओके ओके, मैं राइट लिख ले रहा हूँ।
थैंक यू
Excuse me, sir.
हेलो। हाँ।
Sir, can you explain what is window function, sir? Window function service.
Window function.
Yes, sir.
Right now, I'm not able to explain because I have to read for that one also.
Okay, in assignment they asked a question like which one is the following window function, but in video there is no clear idea about that, sir. So we cannot able to do that in assignment. So that's why I'm asking.
Okay, okay. So window function I will definitely do in next session. Okay.
Okay, okay. Okay.
Thank you.